OffLecture. Learn beyond class.
All right, forget what you see in detective shows. Today, we are the detectives, and our mystery isn't in some dark alley. It's hiding in plain sight, right inside your own kitchen.
I mean, really think about it. Have you ever wondered why a lemon makes your face pucker up like that? Or why soap feels so, well, slippery? And get this, how on earth did our ancestors figure out that something like tamarind could make old copper pots shine like they're brand new?
Well, it's not magic, folks. It's all chemistry. And behind all these little mysteries, there are three main suspects we need to investigate: acids, bases, and salts. Yeah, you heard that right. These three, let's call them characters, they're the ones controlling the basic chemical rules of our everyday lives. I'm talking everything from the food on your plate to the very rain that falls from the sky. So let's get started. Our investigation begins right now. Okay, first things first, let's start by profiling our suspects. We've all had that experience, right? We know acids are sour. You just have to think of vinegar or maybe biting into an unripe mango. But what is actually sending that super sour signal to our tongue?
So let's bring in suspects number 1 and 2. In this corner, we've got the one that makes you pucker up, the super sour acid. And in the other corner, it's total opposite, the bitter and slippery base.
So that sour signal, it comes from a tiny little agent, the hydrogen ion, or H+. It's kind of cool. The word acid actually comes from the Latin word acre, which literally means sour. But here's the real sciencey bit. An acid's true identity, its secret power, only comes out when it's dissolved in water. That's when it releases those H+ ions, and those are the little guys that react with our taste buds. Even the super powerful hydrochloric acid in our own stomach, yep, it works the exact same way. All right, next up, suspect number 2, the base. These guys are the total opposite of acids. They release hydroxide ions, or OH-, in water. But what about that weirdly slippery, soapy feeling? Okay, this is wild. It's because of a process called saponification. Get this, bases actually react with the natural oils on your skin to create tiny amounts of soap, right there on your hand. That slippery feeling is a chemical reaction happening on you, turning your own skin oil into soap. How crazy is that? And here's a little side note for our case file. Not all bases dissolve in water, but the ones that do, they get a special name, alkalis. You've probably heard of one, milk of magnesia. That's a classic alkali we use to calm down excess stomach acid. Okay, so we've got our suspect profiles down. But as a chemistry detective, I can't just go around tasting and touching every random chemical I find. That would be a very bad idea, a recipe for disaster. So how do we identify them safely? Well, we use our most important tool, indicators. So how do these things even work? It's not magic, it's actually physics. Just picture an indicator molecule, and it has a very specific 3D shape, kind of like a key. Now, when an H+ ion from an acid or an OH- from a base comes along and attacks it, it forces that molecule to twist and change its shape. And when the shape changes, the way it reflects light also changes. And boom, that's why we see a brand new color. Now, the most famous one you've probably heard of is litmus paper. It turns red in acid, blue in a base. Simple. But we've also got these cool synthetic agents like phenolphthalein. This stuff is totally colorless in an acid, but the second a base touches it, bam, it flashes this brilliant pink color. And then there's methyl orange, another one, which goes from red in an acid to yellow in a base. And hey, these indicators aren't just for fancy science labs. They're right there in your kitchen. I mean, who hasn't spilled turmeric curry on a white shirt, right? It's the worst. But if you rub it with soap, which is a base, that yellow stain suddenly turns bright red. That's because turmeric itself is a fantastic natural indicator. See? Chemistry is everywhere. All right, so we know how to spot our suspects. We've got the tools, but are they always dangerous? Are they always on? Or maybe, just maybe, do they need a secret accomplice to activate their powers? And their ultimate accomplice is water. Yep, just plain old water. Without it, acids and bases are totally powerless. You can think of water as the key that unlocks their superpowers. For example, if you have dry hydrochloric acid gas and you try to test it with dry litmus paper, absolutely nothing happens. It's a dud. See, without water, the acid can't release those H+ ions we talked about. The water molecules have to literally pull the acid molecule apart. This process is called dissociation. And this This right here brings us to a really key difference: strong versus weak. Now, it's super important to remember this isn't about concentration. Concentration is just how much stuff you cram into the water. Strength is all about how well it breaks apart or dissociates. Let me give you an analogy. A strong acid is like an army commander who storms the battlefield, the water, and immediately deploys 100% of their soldiers, which are the ions. They all go out at once. But a weak acid, like the acetic acid in vinegar, that's more like a cautious commander. Most of the army stays back at the base. Only a few brave soldiers, or ions, are actually sent out to fight. Okay, so now that the armies are on the field, let's see some action. When an acid reacts with a metal, two things happen. A salt is created, and hydrogen gas is released. And there's a really fun way to test for that hydrogen gas. If you bring a lit match near it, it'll make this awesome little pop sound as it burns. But what about the ultimate showdown? What happens when a super powerful acid goes up against a super powerful base? You're probably picturing a huge explosion, right? But the result is surprisingly calm. The aggressive H+ ion from the acid and the aggressive OH- ion from the base, they just get together to form H2O. Yeah, plain old water. They completely cancel each other out, leaving behind a salt and water. And we call this epic but peaceful showdown neutralization. This is all so cool, right? But it does bring up a pretty practical question. We keep talking about strong and weak, but how do we actually measure that power? Is there like a chemical measuring tape we can use to see how strong something is? You bet we do. It's called the pH scale, and the P stands for the power of hydrogen. It's a really simple scale that goes from 0 to 14. Right in the middle, at 7, is neutral. That's like pure water. Anything below 7 is an acid, and the lower the number, the stronger the acid. So lemon juice is down around a 2. And anything above 7 is a base, where the higher the number, the stronger it is. Something like drain cleaner, that's way up there at 13. And trust me, this scale isn't just some boring thing for the lab. It's absolutely crucial for survival. Our own digestion needs a very specific pH. You know when you get heartburn? You take an antacid, which is a base, to neutralize all that extra stomach acid. The pH of rain, of soil, that determines what can even live and grow. Nature even uses it for defense. Think about a nettle plant. That sting is it injecting acid right into your skin. Okay, let's jump back to that neutralization reaction for a sec and meet the kids, the salts. Now, a lot of people think all salts are neutral, like table salt, but that's not true at all. A salt's personality, whether it's acidic, basic, or neutral, totally depends on the strength of its parents. So if a strong acid parent overpowers a weak base parent, guess what? The baby salt is going to be acidic. So now that we've met the whole family, acids, bases, and their offspring, salts, let's close out our case file. And we're going to do it by looking at salts not just as leftovers from a reaction, but as the real unsung heroes of our everyday lives. I mean, just think about it. Baking soda? That's a salt. It's what makes our cakes light and fluffy. Washing soda? Another salt. And it helps our detergents clean better by softening hard water. And plaster of Paris? You guessed it, another salt. It has this cool hydration reaction where its crystals lock together to form a rock-solid cast for broken bones. Amazing. And now it's time for your final challenge. We all know pickles are acidic, right? So why should you never store them in a metal container? Come on, think about it. What did we learn happens when an acid and a metal get together? All the clues are right there in what we just talked about. Now go on, get out there, and start seeing the world through the eyes of a chemistry detective.